This is lecture 15 of Physics 210A, Thermal Physics. And this lecture is going to be problem solving session number 6. And we are going to solve problems based on whatever we have covered in the previous 3 to 4 lectures. Problem 1. This is taken from Atkins's Physical Chemistry. And it says, suppose 3 times 10 raised to minus 3 moles of nitrogen occupy 36 centimeter cubed at 300 K and expand freely to 60 centimeter cubed. Calculate the change in its Gibbs energy. So the solution is delta G is nothing but delta U plus P delta V minus T delta S, and we are going to perform our calculation assuming that the gas is ideal. Now, since this is expanding freely, there is no work done. So, number 1, P delta V term is going to be 0 and is connected to the environment at T equals 300 K. So, since this is ideal gas, delta U is also 0. And therefore, delta G is going to be minus T delta S. And delta S is calculated only considering the change in the volume. Therefore, this is going to be minus T. And for an ideal gas, changing from volume V1 to V2, that's the entropy change, and this is going to be minus nRT log of V2 over V1. And you plug in the numbers, this comes out to be minus 3.8 joules. So as this does this spontaneous process, there is the Gibbs free energy reduces. I want you to show this. Next, calculate the change in Gibbs energy of ethanol. Its mass density is 0.789 grams per centimeter cubed of mass 35 grams when pressure is increased on it from 1 atmosphere to 3000 atmosphere. This is also taken from Atkins's book. And the solution is using the equation for dG, which is V dP minus S dt. And since the process is isothermal, dt is equal to 0. So we are going to calculate dG as V dP. Now this is ethanol, this is liquid, so we are going to assume that this volume does not change much when we increase the pressure, although there will be some change. So work, whatever we are calculating, is going to be slightly higher because next the volume is going to be smaller. So that work is going to be slightly higher, whatever we calculate, compared to the actual work. But still, we just assume that V is constant. So that gives you delta G equals V delta P, and volume is 35 over 0.789 times 10 raised to minus 6 meter cubed times 2,999 atmosphere. So I can remove this atmosphere, write this 10 raised to 5 Pascal. And that gives you 13 kilojoule. That's the answer. Actual one could be slightly less. Now I'm going to go to problems which are different from the gas problems, because remember what I had said at the beginning of the course, that thermodynamics is quite general. It can be applied to any macroscopic system. So next I'm going to focus on magnetic problems, because if you recall from those previous lectures, we had also said that we can apply this to dielectric materials, we can apply it to magnetic materials when we do some work on them by applying magnetic field, by applying, changing their magnetic moment, or to the dielectrics by applying electric field and changing their dipole moment. So I'm going to now focus on magnetic systems to show precisely that application of thermodynamics. So next three problems that I'm going to do are going to be on magnetic systems. So I'm considering magnetic systems which are weak paramagnetic salt. And by that what we mean is that their susceptibility, the magnetic susceptibility, is much less than 1. I'd like you to recall Physics 103 here. So we can say that implying that chi m plus 1 is almost equal to 1. Now, in such cases, when we take field B inside a magnetic material, it is equal to mu relative B applied, which is 1 plus chi m B applied. Let us call B applied B 0. So, this is almost B applied, and we are going to take this to be B 0. So, first problem that I am going to solve with this background is problem 3. Is consider a paramagnetic salt with chi m much less than 1 in an applied magnetic field B 0. Assume that the volume of the material remains unchanged when the field is applied. Then we want to show that the entropy of the system with respect to the applied field, change in the entropy of the system with respect to applied field, if you keep the temperature the same, is equal to partial m over partial T when B naught is kept the same. And in the process, we will also derive some other Maxwell relations. So, let us solve this problem. So, remember, what is the change in the internal energy? This is equal to T ds minus P dV plus the magnetic work done on the system, which is going to be B 0, because we are taking B 0 and B to be the same, d, the magnetic moment. And we have already said that dV goes to 0, and therefore, we can write du equals T ds plus B 0 dm. So, internal energy goes up on two counts. One, we supply heat to the system, and we do magnetic work on the system. And this tells you that partial U, partial S at constant magnetic field is equal to T, and partial U over partial magnetic moment at constant S, that is under an adiabatic process, is equal to B 0. And again, since U is an exact differential, this implies that partial T, partial M at constant S is equal to partial B 0 over partial S at constant M. This is one of the Maxwell relations. But this is not what we had asked for, so we going to do other things. Now, next, we define Helmholtz function f, which is u minus ds. So, df is going to be du minus t, ts, tds minus s dt. And du minus s dt is bu minus tds is b0m, because I have du equals t ds minus b0 dm plus b0 dm. So, du minus t ds is equal to b0 dm. And therefore, df is equal to minus s dt plus b0 dm. And this gives you partial of f with respect to t at constant m is equal to minus s, and partial of f with respect to m at constant t is equal to b0. And the corresponding Maxwell relation is going to be minus ds over dm at constant t is equal to db0 over dt at constant m. Let's go to the third one now through the Gibbs free energy. So, define Gibbs free energy as u minus ts minus b0 m, and this gives you dg equals minus s dt minus m db0. I have not done the steps in the middle, and therefore, dg over dt at constant b0 is equal to minus s and partial g with respect to b0 at constant t is equal to minus m. And this gives you the Maxwell relation partial s over partial b0 at constant t is going to be equal to partial m over partial t at constant b0. This is the relation that was asked in the problem, but in the process we have also gotten 2 or 3 other relations. Next, I am going to apply this Maxwell relation in a problem. So, we are going to say this is from Finn's thermal physics, and it says use one of the Maxwell relations obtained above to show that during an isothermal, and reversible. Magnetization. The heat produced in a magnetic sample is Q equals CV over T square mu 0 B 0 square over 2. So, let's just look at the analogy from the gas system. We have written for magnetic system T, ds equals du minus B0. dm of the gas system is T ds equals du plus P dV. So, in a way, this P is like minus B0 and V is like M. If I'm magnetizing a system, I'm increasing B0, minus B0 is decreasing, and the system is expanding in the gaseous system. Now, what we are saying here is that I'm magnetizing a system under isothermal conditions. So, under isothermal conditions, the system, when it expands, then it absorbs heat. Now, in the present case, what we are doing is we are doing work on the system. Work is not being done by the system, its work is being done on the system. So, it's pumping in work, and that, if I want to keep T the same, may result in the system releasing heat to the outside. So, this is how you can make an analogy in your mind. Now, we are going to assume in this that paramagnetic salt has chi m, which is C over T. So, let's now solve this problem. The heat Q going into the system is given by dq equals T ds in a reversible process, and that is the kind of process we are considering. So, what I need to calculate, if I calculate ds and integrate it, then we are done, because then delta Q, since T is going to be delta S, since T is constant. So, we need to calculate delta S. For that, let's consider S as a function of T and B0, because I want to use one of the Maxwell relations, and write ds equals partial S partial T at B0 dt plus partial S partial B0 at T dB0. So, since this is an isothermal process, this is 0. And therefore, I can write ds is equal to partial s partial b0 at constant t db0. Now use the Maxwell relation derived in the previous problem, ds db0 t is equal to dm dt b0. So you have ds is equal to partial m over partial t at b0 db0. The magnetic moment is going to be volume times the magnetization, which is nothing but V times 1 plus, which is going to be V times chi m times h, and this can be written as V chi m h is B over mu which can be roughly taken to be, because chi m is very small, V chi m B0 itself. Now you're given that chi m is equal to c over t, and therefore m equals v c chi m b0 over t. Partial m over partial t at b0 is going to be minus v c chi m over t square b0, and therefore delta s is going to be equal to minus v c chi m over t square b0 db0 integrated from 0 to some value b. This comes out to be minus v c chi m over t square b square over 2. Negative sign meaning that heat goes out of the system. It goes out because that's how the system remains at constant temperature. So heat produced is Vc over mu naught. There is a mu naught also somewhere. This is mu naught here. This should be mu naught here, mu naught here, mu naught here. So it's Vc chi m over mu naught t square, b square by 2, where b is the applied field. And negative sign means it's going out, that is the heat that is produced, and then it's taken away to keep the sample at constant temperature. So with this, I'll conclude this lecture. We have solved problems related to Gibbs energy, number 1. Number 2, we have applied thermodynamic relations to a paramagnetic salt being magnetized. Now keep in mind, when I'm magnetizing it, then the system heats up. So if I demagnetize it, it may cool down, and that is a kind of problem that I'll give you in the assignment. Thank you.